Ladies and gentlemen, welcome to the session about planning table indexes for the best performance. Please give them a warm welcome, Alexander and Stefan.
Thank you very much. From my side again, hello and welcome to our session. In the next 90 minutes, Alex and I will try to explain to you or give you an overview about what table indexes we have at our disposal in Business Central and what we can do to achieve a little bit better performance on our queries.
Hi, I want to join Stefan in saying hello, good afternoon to everyone. Welcome to our session and thank you for coming. A few words about who we are. I'm Alexander, Microsoft MVP. I work as a solution architect for LS Retail, and among other things that I do, I'd like to emphasize one thing. What I like to define as making the application run faster. So I work with performance. Behind this QR code on the screen, you can find my blog, where I also write about Business Central development, and mainly also about around the same topic, Business Central, with SQL Server and performance questions. And this is pretty much what we are going to talk about today.
Okay, my name is Stefan Marón. I'm a freelance BC developer. I'm also a BC MVP since last year. You may know my GitHub project, the code history on GitHub, and also the sandbox history. Occasionally, lately not that much, but I try to pick that up again. I do code streaming, live streaming on YouTube, just explaining concepts as I go. And you can find me on Blue Sky, on Twitter, on my blog, and let's get started.
And to start with a little bit of a funny note, I'd like to introduce the session with this quite famous now quote by Michael Swart, who is a SQL Server expert, used to be an MVP in SQL Server some time ago, and a while ago he coined this phrase, which has become famous by now, I believe. If you're using over 10% of what SQL Server restricts you to, you're doing it wrong. And this applies, very strongly applies to indexing. And when we're, I would say even 10% of what SQL Server restricts you to when it comes to indexes is even too much. We can create up to 1,000 indexes in SQL Server. If we have 100 indexes on a table, probably we're definitely doing it wrong. So this can be like a punchline of our presentation. So that when we talk about indexing, when we talk about performance and planning the indexes, we should consider it from every point of view. At every time we add an index, we may improve performance of some data retrieval query, but on the other hand, we're very likely to break something and slow down insert, for example. So with this in mind, we'll start.
Okay, one word of caution right away. We have, I think, over 60 slides. We don't have any demos because we don't have any time for demos, because from now on we will start talking a little bit faster to make it through all the content we have. So it might look a little bit like this. It will be technical from now on. So this is the agenda we came up with. First, we'll talk a little bit about indexes in general, what it is, why even, and some ups and downs related to indexes. So we get all on the same page. And then the main part, we will go through all the index types we have at our disposal in Business Central, as I said in the beginning. There are quite some of them, and we will talk about their ups and downs as well, give some examples as good as we could, to give you a feeling of which index can be used for which scenario and what is it good for, what is it bad in. Afterwards, I have a small section for trying to explain a little bit the way we created the examples, how to check the index yourself, whether it's used or not, whether your query fits to the index you created or the other way around. And at the end, we'll just sum up a little bit, give some general considerations when it comes to indexing, and then we'll just wrap everything up again a little bit so you don't leave more confused than you came here in the beginning, maybe.
I believe most people here know what an index is, right? How it works when it is used. But I still believe that it is worth spending a few minutes to recap, let's say, speaking about the very basics. What is an index? And basically principles of indexing a table. So in the most broad definition of an index, it's any data structure that supports faster data retrieval, data access. When we talk about an index, the most common understanding, the most commonly used type of an index is a B-tree structure, right, which is implemented in SQL Server as a B-tree. We can think about this index by an analogy. Imagine it like alphabetic index in a book. Think about an encyclopedia. When you want to find a word in a book, you sure don't want to leaf through the whole book, read the whole content of the book if you want to find the one word. You can open the alphabetic index where every word will be sorted by the alphabetic order, and the index will point you directly to the page where you can find the word that you need. That's the most common analogy, and it's pretty much accurate, I would say, when we're talking about one kind of indexes, specifically B-tree index. But as we will also talk today, not every index is made equal. Some indexes are based on different data types, different data structures, intended for different types of workloads, but still the basic principle remains. An index is a data structure that facilitates data reads.
Exactly. And this is one picture I came across which pretty much explains it a little bit better. So when you need to think, like he said, of a tree structure. So we have that entry point, and then it gets more detailed, the more levels we get down in that tree structure. And how big those pages are and everything, that's internals we don't really need to care about. But as you have more data, larger keys, this tree structure will grow. So when SQL Server starts searching for a value, it will always start from the highest value from the leaf, as you can see in the picture maybe. And then now if we take an example and simulate just how SQL Server looks for a value, if we take 57 as our sample value, it will go through the leaf it's looking at. It will search in ascending order until it finds a value greater or equal than the one it's searching for. And if that's the case, it will go one level deeper and continue until it can find that value it's looking for. And then on the right-hand side, next to the 57, on the lowest level, you see that B1, C1 thing. That's basically the reference to the main table to read all the different data, the remaining data for that specific record, because an index does not contain that by default.
So when do we want to use indexes? As Stefan just showed in his example, well, obviously, when we want to find some specific piece of data, pinpoint a record in a table, a small subset of a table, like getting a custom record, filtering a few records in a table, searching. So in this case, instead of, like that book example, instead of scanning, reading the whole table, comparing every value with what we're looking for, we can use this index structure to quickly descend to the value we are looking for. It works perfectly when we need to aggregate a small amount of data. We can think about it again as a special case of the first example. When we run a calc sums expression, for example, and we need to summarize just a few records. Basically, in the backend, what database engine needs to do is find those records that must be summarized, read them, and calculate the amount. This calculation can also be based on an index. Flow fields, for example, can work on the same base. We can consider SIFT views even as a special case of an index. We will be talking about it as well. It's not exactly an index, but we'll talk about it a little bit as well. And that can facilitate reads and aggregations very much. Sorting, whenever we need to read the data in any ordering other than the default primary key, again, indexes can help here.
Okay, and then just to get, again, everybody on the same page, we have two words we're juggling with, which is keys and indexes, and both mean something, and maybe something different in SQL Server versus Business Central. So in SQL Server, a key is not an index, but an enforcement constraint, basically. So we can have a unique key, for example, which will enforce that a certain column stays unique in SQL Server. And an index is the tree structure we showed before, which improves performance of data retrieval. Now in Business Central, a key is basically an index definition. If we mark it unique, it's also a key. So there the confusion starts maybe. And then the primary key in Business Central is both. It's a primary key constraint and a clustered index by default. So just so we have that on one slide at least.
And a little more about keys and indexes. As was just said, that one special case of a Business Central key is the primary key, because special, in the sense that every primary key in Business Central is a key and an index at the same time. There are more like this. First of them, of these kind of keys is system ID, which is an alternative identifier of our table row. Right? So it is also a key in the sense of SQL Server, unique constraint. And it's also an index. So by default, in every table in Business Central, we always have two keys on SQL Server side, which is primary key and system ID with indexes built on these keys. Beside these two, we can always create any other key just by setting the unique property on any Business Central key. So every other key except primary key and system ID is always an index, except these two are keys and index at the same time. And if we set a unique property on a Business Central key, we create, again, index, which is a key at the same time. This will help us enforce the uniqueness, ensure uniqueness of the value within this key, and basically works as an index as well.
Okay, then two more words we need to talk about first. We have seeks and we have scans. Now the seeks, as the word suggests, it's searching data and it's not scanning and everything. So a seek uses the index structure, like a binary search. It's fast because it can make use of the index of the tree structure and jump to the desired data, opposed to just reading through everything and searching it that way. So it's really using the index, but it requires selectivity, so we have to have like a filter or something to even be able to have a seek on SQL Server. Now, and scans is the opposite. That's the if no seek is possible, then SQL Server will do a scan. That can either be an index scan or a table scan, but it will read through everything and figure out what it has to find that way, and not select what it can through the index. Yeah.
Oh, well, so far so good. We're talking about very positive effects of indexes. They definitely help us increase the speed of data retrieval or the finds, but every good thing has its reverse side. Right? Indexes have a flip side as well. So when we're talking about indexes, we need to consider not only how much they improve the speed or increase the speed of data retrieval, but how they impact on other aspects of database maintenance and data updates as well. And in this sense, indexes can have negative impact as well. First of all, on data updates. Any insert, update, or delete operation has to update, respectively, all the related indexes on the table. So that's one thing we need to think about. Whenever we have an index, we have a higher probability of lock-in issues and session contention. This problem is to some extent mitigated in Business Central, because in Business Central, every index is always unique. And so we don't have a chance to insert, we don't have the possibility that two concurrent sessions can update the same value of an index when they insert different entries, for example, because index values are always unique. But still, it's not 100% ruled out. And when we're talking about wider understanding of an index and include SIFT, for example, in this case. This can be a major problem when we're talking about SIFT views. Indexes consume storage, which we'll also talk about and show an example here. And finally, indexes require maintenance. Not something we need to care about when we run, when our Business Central instance runs in the cloud as a service in SaaS. But still, maintenance jobs consume resources, can create a resource pressure, and slow down concurrent sessions. So not everything is so perfect. Will it switch?
Yeah, and then before we jump now to the main part, just a short recap on the introduction. Indexes, we create indexes to increase read performance. We get faster data access, but we have a trade-off of slower writes, maintenance, size. So we need to consider when to create, like we need to decide from case to case whether we want to create an index or not, if it gives us enough benefit to live with the trade-offs. So that's now the main part, going through the different index types and figuring out what they're good for. First one, row store indexes. We have Columnstore, this is row store, and the clustered index, aka primary key, is the first one. There we go.
Mm-hmm. So when talking about clustered index, it's not that much about pros and cons, benefit of the clustered index, if we should use it or should not use it. We just don't have any other option except, yes, we have it. It exists. Although in SQL Server, it is possible to have unordered heap tables without the clustered index. It's not the case for Business Central. There is always the clustered index. So we're talking here about the clustered index. Just to be on the same page, we will be referring to this concept multiple times throughout the presentation, just to introduce what the clustered index is and when it is used. Essentially, clustered index is the same B-tree structure that we were talking about, with one important difference from every other index. Leaf nodes of the clustered index, leaf nodes of this tree contain the table data itself. Basically, clustered index is the table. It defines the physical ordering of the data in the table. And since the data in the table on the hard drive can be sorted only in one single way, the clustered index can be only one. So in Business Central, there is always only one clustered index. There must be one. And of course, there can be no more than one. We always have a clustered index. Clustered index is the one that has the property clustered set to true, usually. Although it's not mandatory property, right? We can omit it. And in this case, if we just don't specify this property value clustered, or even if we explicitly set clustered to false in every key, then the default first key in the list will be the clustered index. There is a little misunderstanding here, I would say. Sometimes people think that moving the clustered index to some other key, like not the first one, by doing this, we change the primary key, which is not the case. It's not correct. We can change the clustered index, but we cannot change the primary key in this table, meaning that the first key in the list is always the primary, but the clustered index doesn't have to be declared on the primary key. It's just the default value. And the clustered index, when is it used? Well, assuming that we have the default setup and clustered index matches the primary key, whenever we call a function like get, retrieve the value, it will be searching the data based on the clustered index. Right? When we apply a range filter from value to value, if this range results in a large number of records being retrieved, which constitutes a significant portion of the whole table data, then the search is likely to be on the clustered index too. So these are the cases when the clustered index is used.
Exactly. And now one example, I mean, it's pretty basic code. We just get one item. And then I hope this is readable. This is an execution plan for if somebody didn't see an execution plan before, which is basically the way of SQL Server telling us what's happening under the hood. It's possible to activate this. I will show later how that works. And what we can see is basically that SQL Server uses clustered index 6, 2 of them, to retrieve the data, because all we do is get that record from the item table. So it will go through the main table, and because we don't have set load fields and we have probably some table extension on the item record, it will also read from that extension table and then merge them together and give us the result. So that's the clustered index seek. So it doesn't need to do a scan here. It can use the primary key because we give the primary key value and do a seek, which is not even that bad. And now, still row store indexes, but now the non-clustered index. So everything that's not the clustered index will be non-clustered indexes, basically. And it looks like this.
Yeah. And now we're coming to something more interesting. Essentially, as Stefan just introduced, every other index in the table which is not clustered is basically non-clustered, unless we decide not to maintain the index at all, not to create an index at all, and set the maintain SQL index property to false. Why would we do that? But yeah, we can do it. Maybe we just want to create a SIFT view without an index. Okay, we can do it. What differentiates the non-clustered index from the clustered index? As I said, the clustered index itself is the table data. So when we dig down into the leaf nodes of the clustered index, we find the table data. While non-clustered indexes will have pointers to the clustered index, actually pointing to the data.
Yeah, I think we'll see that later in a picture.
A SQL Server table can contain up to 999 non-clustered indexes. Business Central limits us to only 40, but even this 40 is a large number. So we can even here we can apply that Michael Schwartz rule, 10% rule. If we create more than 4, 5 indexes, maybe it's not strictly no, but something to think about if we need these indexes. When these are used, well, basically all the examples before that we were talking about. Non-clustered indexes used when we want to facilitate searches by non-primary key fields. Right? When we filter any table opportunity entry, in this case, just select it randomly on the opportunity number, this is likely to end up in a non-clustered index seek. When we want to filter data, when we want to sort, when we want to extract the data from a table ordered by any field other than the primary key.
Okay, and then how much faster is it actually to use an index seek instead of a scan? And yeah, the red one, we are seeing the red line, which is pretty linear. It goes just up, but with the number of records we have in a table, that's a scan. So if we need to search through all of the records in a table, it will just get slower as like the more records I have in that table. The index seek, on the other hand, the bottom line, the blue line, this is more of a logarithmic increase. So it still increases with the number of lines I have in that table, but it's not as sharp and not as consistent, so it slows down the more records I have. It still goes up, but not as fast. And then obviously, not only the number of rows in the table play a role, but also like how many rows actually the query returns, also the distribution of values. So there are many factors which brings us to our, I think, leading word in this session. It depends a little bit, so you need to try. Yeah,
that's
and
pretty much.
Storage hardware and probably a bunch of other factors as well. So, but in general, if we can make the query use an index seek instead of a scan, it will be faster and it will not be as dependent on those factors as the scan is.
And the more data we have in the table and the more data we select, the more difference we will notice.
Exactly. And then now we have a chart of how inserting is affected by different types of indexes. So the lower bar, the blue one, is basically no indexes. And now I need to look at the bigger picture. So we have just over 20 seconds in that example, in the demo table we came up with. And now if we add 5 or even 10 indexes, you can see that the times go up to over 50 seconds. So we have like more than double of time it takes for inserting the records just by adding indexes and not even like having much logic behind it.
And again, to add another, it depends in this case. These test results are reproduced in a single session. Right? The inserts were done just in one session and pretty much sequentially. This, again, very much depends. Like, take it with a pinch of salt, of course, this picture. It doesn't mean that, well, whenever you add an index, the time will be incremented by a certain amount. It depends on how this data is distributed, very much. If you are inserting values sequentially or randomly interlacing order. But we can think about it as a rule of thumb. Take as a rule of thumb, let's say that with every added index in a table, the insert or update time can increase by 10 to 20% sometimes.
Yeah.
And again, then it depends.
Yeah, and slower updates essentially mean increased probability of update conflicts and log timeouts, because if a session is running longer, it will take that, like it will hold that log longer, and then other sessions have higher probability of hitting the same records at the same time, which will reduce in log weights. So.
Okay, so just now we talked about one negative effect of having an index. But on the other hand, having an index on a field on a table does not necessarily lead to the improvement or like faster data retrieval, or at least not in the sense we expected every time. What I want to show here, what I call my one counterintuitive example, is where adding an index on a table does not lead to the expected result. So here you see a pretty simple query. It's an aggregating group by query that selects data from a table, which I called my table with indexes, and this table has fields, dimension value, and amount. So basically, in this case, I want to group amounts from this table by, summarize amounts by dimension value. And despite the name of this table, my table with indexes, actually, right now, for this test, this table does not have any indexes. If dimension value 1 is not indexed. I run the table, or pardon, run the query, and get the results. It takes the query to complete like around 260 milliseconds. Okay, but I know that right now my table is not indexed, but indexes are good. If I add an index on the dimension value 1, it should improve my query. It will be faster, right? Let's see. I add an index on the table, and the query runs almost 2 seconds. Why? What's going on here? I expected it to be faster. Instead, I see it many times slower. Actually, to answer this question, we need to dive a little deeper and answer another question. What does faster mean? Well, you may say, what a weird question I'm asking right now. What do you mean faster? We just measure the time, take the time when the query started, when it ended. That's the execution time. We compare this time for multiple queries, and one that has shorter runtime is faster. Well, yes and no, because this is only one way of defining faster. And this, in this case, we prioritize the complete query execution time from start to end. We can instruct the query optimizer that we want to prioritize complete result over partial interim results. But there is another possibility, another way to define faster. And another option is prioritize faster interim partial results. In this case, the query optimizer selects the execution plan in such a way that the partial results can be returned immediately, as fast as possible, so that Business Central, or actually, this is pretty much an abstract example. Any client receiving data from the database can start processing the data immediately, while SQL Server still continues running. The query is still running at this time. This way, it allows to parallelize the workload between the client and the server. Partial results can be made available pretty fast, but on the other hand, this can be contradictory to the first. And the overall query execution time may drop, on the contrary, the time will increase, the performance will drop. So query will be slower, actually. And these two options pretty often contradict each other and result in very different execution plans. So now back to the question, why my query is slower? How does Business Central define this faster? And in Business Central, faster means exactly the second option. Business Central, in this sense, goes the second avenue of prioritizing interim partial results. So in every query that is generated from AL code that is sent from Business Central to the SQL Server, there is this option FAST50 added, which means that we expect a SQL Server to return the top 50 rows as fast as possible, while the rest of the query, well, we don't care that much about. It can be way slower. That's what I was talking about. The query result will be, the total query result will be received later and slower. And in case of my index on the table, when I added the dimension, index on the dimension 1, this index allowed the SQL Server to run a seek operation, or actually it was a scan, really, on the index that I just created and return the top 50 rows very quickly. But the overall time, well, is not so efficient, not so great, compared to option 1, compared to the non-indexed query. And this result, by the way, the result is something that we can reproduce on SQL Server 2019 and later with parallel batch mode execution on row store. Because in this case, when I run this process on a non-cluster or non-indexed table, this results in a parallel execution plan. And the scanning of the clustered index in parallel threads can be much, much faster. But on the other hand, this blocks these interim results. We have to wait all the time until the query is completed. So you see, in this pretty much contradictory example, we see that we need to understand what it means for us and for Business Central architecture and for SQL Server, what it means to be faster. Sometimes, even adding the index, we can come to an unexpected result. Maybe from the point of view of the general resource consumption of the execution cost, the clustered index scan will still be more expensive in terms of CPU time, input-output. But if we look at it from the total query execution time from start to end, well, it's still way faster.
That means it depends again, right?
It depends again.
Okay, continuing. Well, we'll continue in the same area. We're still at row store indexes. We're still at non-clustered indexes. But now we'll talk a little bit about what covering indexes are and how it connects with included fields property, which we got not too long ago. So this is the chart I promised you before. So on the right-hand side, we have a non-clustered index, which contains just the index definition, right? No details, just the nodes, the index column we defined to be able to search for the records we're looking for. Now, if we have a non-covering index, what it means that the query SQL Server has to go through the non-clustered index, find the records we're searching for, and then it will need to do a key lookup and look into the clustered index, the actual table, to retrieve the connected table data with the additional columns we need, which are not defined in the index. Now, as soon as we add included fields, or if the index fields itself supply the data we need, then we can eliminate the key lookup completely and save a lot of time, actually, because then the non-clustered index has all the data we need to have our query return it to us, basically. So it doesn't have to read a second time into the actual table.
Okay, so speaking about the covering index, just like if we try to define it, this will be an index that can provide all the necessary data for the query from the non-clustered index itself, without the need for a key lookup, for lookup into the clustered index. And in this sense, covering index is not some kind of a special type of an index, something abstract. It's always a covering index for a certain query, because something that provides all the data for one type of a query will not work for a different query, right? So clustered index is always, covering index is always a covering index for a specific query. And in this sense, we can say vice versa, the query will be covered by a specific index. As we will show now in a couple of examples, when we plan a covering index, can look at at our structure of our code and the resulting query. Those fields that will be filtering on and will be present in the where clause of the query should be indexed, present in the B3 structure, while everything else, basically all the selected fields, everything present in the select clause, can be added as included fields. And this is why covering indexes are often associated with included fields, because practically this is what included fields property is used for, right? When we want to provide all the data necessary for a kind of query, we can add everything into, well, have all selected fields into these included fields.
Exactly. And there are a few things to note about the difference between FindSet and the query object in Business Central. Now we need to be careful to not say query without object if we mean the object, because it gets confusing. So the FindSet function includes additional fields in the select clause. So first of all, we have obviously all the fields we define in the setLoad fields. If we don't define setLoad fields, we just have all the fields, but that would be hard for covering index. So we define setLoad fields, we have the fields we define there. We have system fields, the timestamp, basically, in I think it's row version in AL. We have the system ID, the created by, created on, modified, and so on. We have fields which are filters applied on, the primary key. We have fields that the runtime decides are necessary. Maybe we had a JIT load and it added a few more fields to the select query. Maybe there are event subscribers with different functions adding fields to the loaded fields we defined. So it might be possible to add fields at runtime. So for a FindSet, we never really know what fields will be selected. So it's virtually almost impossible to have a guaranteed covering index. Now with the query object, it's easier. We have the columns we define and the primary key fields. That's it, nothing more. So it's way easier to define an index with included fields to get a covering index for query objects than it is for a FindSet. Same goes obviously for find first and find last, all the other ones.
And a couple of examples here. For example, that code snippet, let's assume I want to select a set of like bunch of records from value entry table. Well, first of all, I want to apply filters. Obviously, I don't want to select the whole table, so I set filters on the source type, source number, and these are the fields that I want to be indexed, present in the B3 structure. So this is where what I defined in my key. I'm just picking a key from the value entry table itself. But for this specific example, I don't need basically anything else in the index itself besides source type and source number. And then I have the list of fields which I want to select, which will be in my select clause. These are invoice quantity, sales amount, discount amount, whatever. Those will be the fields that I can keep only in the leaf nodes of my non-clustered index. This will be included fields. And to illustrate the difference that Stefan was talking about between FindSet and a query object, if I run this FindSet from that code snippet in the previous slide, you see on the left-hand side here, yeah, thank you. Here on the left-hand side, we see the key lookup, exactly because FindSet will add a certain number of fields, which I didn't expect to find there, probably. Well, I did, but they're not covered by this index. And in this sense, this index that was supposed to be maybe could be covering for this query appears to be not covering because it's not sufficient to retrieve all the data. When I run a query object, on the other hand, define the same columns and the same filters here on the right-hand side, we see a pretty much different execution plan. It's only index seek. I have a sorting as the most expensive operation here, which can be, again, eliminated if I change my query and add order by property, sort. Then the sorting can be removed as well and be even faster. But even like this, just removing the key lookup and provide the data from the covering non-clustered index, you see, we have pretty good performance improvement already. In this example, I don't even have this good covering index. It's kind of an imperfect index. My data that I want to select is split between two indexes, actually. So I select data from item ledger entry table, which I filter on the item number. And I have two, like not I, but these are two keys from the base application as well. Two indexes with the item number field, which is indexed and present in the whole B3 structure, and the data that I want to select. Document type, document number, location, quantity, but this data is split between two indexes actually. So there is no one good covered index that can provide all the data for me. How will it work? Well, not bad actually. Same situation, similar. When I run find set, the database engine still has to do a lookup into the clustered index to retrieve the data. If I replace it with a query object, well, of course now I have two separate indexes because there is no index, no single index that can provide all the data that I need. And in this case, SQL Server has to do this hash match, building a large hash table to collect, to join all this data. But still, it is more efficient than the key lookup. Okay, so that's an illustration of a covered index and how we can use it actually with query object versus find set. So far, so good. Covering indexes are really good and can be really good performance booster. But what we need not forget when we're talking about covering indexes is the size, space that it consumes. Usually when we build an index, normal non-clustered index without included fields, we include 2, 3, 4 fields, right? It wouldn't be really huge because the more fields we add to an index, the less efficient it becomes. In case of covering indexes, pretty often we need to add a large number of fields to the index as included fields, and these take space. Here, let's say I have a table that had like 2.77 gigabyte of clean data without indexing. Adding just 5 fields to 3 indexes on this table increased the total size from close to 4 gigabytes, from a little over 3 gigabytes to almost 4, 21% growth. Just 5 fields in 3 indexes. And this can be quite expensive. We know that space, like storage space, is not really cheap in SaaS, in Business Central. So this is something we need to take into account. Covering indexes can be good, really good performance booster, but they require some space. I need to keep an eye on it.
Okay, now let's see an example for covering index. Here we have a very simple query at the top, GL entry. We set GL account number and posting date as the fields we want to receive from the database. We do set range on the account number. Now imagine this would be a parameter or whatever, not hard-coded of course, and we do a find first. Now the key we want to use for this, or we envision that SQL Server would be using, is the key number 2, GL account number, posting date, right? Pretty simple. We don't even need the included fields we have here because the key fields itself would already be covering. Now if we look at the query that results from that piece of AL code, from the find first, we see this. I tried to format it a little bit so it's readable. And we want to have GL account number and posting date, and all the other things which are highlighted in red are things we don't really care about. We don't want timestamp, entry number, all the system fields. I don't know where source type is coming from, balance account type. I don't even know. And we don't necessarily want to have it ordered by primary key either, because who cares? So the thing is, in order to fulfill this statement on SQL Server, in the execution plan, we see clustered index scan, which is basically reading the entire table because there is nothing that can really serve this kind of query. Now, if we look at the same representation of data retrieval basically with a query, as we explained before, so I'll do the set range on the GL account number, top number of rows 1 because of the find first, open, read, and the query definition says just the 2 columns I care about, and I also set the order by for the same fields I have in my index defined. Then the query looks like this. I just have top 1 again. I have the GL account number at the top, posting date, entry number, because primary key will also be read. I do have an order by still, but it's the same as my key, basically my index I created. And then the execution plan looks like this. I have an index scan without a sort operation, without anything, which is blazing fast. Now, it says 0 seconds because I don't have much data, but yeah, this makes full leverage of the index in this situation. And basically, AL-wise, there is virtually no difference that's happening, except for, well, I have another query object, but in terms of logic, there is not really any difference. Now, let's get started on SIFT keys.
It's getting more and more interesting. Now we're at SIFT. So I said already in the beginning that SIFT is kind of very different type of beast in Business Central. It is not an index as such, right? But still, we need to talk about it, of course, because on our minds of AL developers, SIFTs are so closely associated, so tightly bound to index definitions, to the keys, right? And besides, it's a very good, very common, very typical way of facilitating aggregations in AL. So of course we can't let it sleep. We need to talk about SIFT as well. So if it's not an index, then what is it actually? SIFT is in fact an indexed view. See, the word index is still here, so we need to talk about it. It is an indexed view, and if you don't know what an indexed view is in SQL Server, you can think about it as a kind of a table, which is automatically updated, maintained by the database engine. This table, it is actually a stored table in the database. Practically almost in every account, it is a table, with some caveats, quite important, which I'll be talking about too in a minute. This table contains aggregated data. All the summaries, all the sums, counts that will include in the SIFT definition. These aggregations are updated whenever we update any data in the table where the SIFT is defined. Right? So if we have a SIFT defined on the customer ledger entry table, when we insert any new record in the customer ledger entry, all associated SIFT views will be updated as well. We don't usually delete or update any records in entry tables, right? But if we were to, same way, the database engine SQL Server itself would take care about updating associated SIFT views. All the data is always pre-calculated during create, update, delete operations. And this way, we're pushing all the calculations from the read side, all the aggregations, from the read side into the write side. And this makes SIFT so efficient in reading aggregations, because there is no calculation when data is retrieved. All this calculation is done when data is actually updated. On the other hand, the same fact makes it so bad for updates. We will see in a minute. And functions like count, calc sums, or calc fields can take advantage of the SIFT views. So when we have good fitting SIFT defined on the table, when we want to calc sums from the same customer ledger entry, let's say, the query will be actually directed to the SIFT defined on it. Automatically, we don't have to care about, don't have to think about it. It will be done under the hood, behind the scenes. We don't even know what's happening. And just to illustrate what it is, we can indeed even open SQL Server Management Studio and look at the data in the SIFT. Can run a query against it, see that all the data is stored. It contains all the calculated, for every combination of vendor and posting data, it will have store a combination, a sum of the amounts and even the count. This way, the functions like calc sums or count can retrieve data directly from this table.
Yeah, now, how fast is it? So when we run a calc fields with the filter on one single field, on the very left side, that big blue bar here is the field is indexed. So it's not even the not indexed. If we put that on a slide, then we don't see those bars anymore. So we have an index, and that's the blue bar here. Now, if we were to add a covering index with all the required fields, then we already go down to the red bar here. And I think this is in milliseconds, so we are at 50 milliseconds then. And then the SIFT keys even take it one step further and bring it down to the yellow bar here. So I think it's almost half the duration again of a covering index. So in reading, it really outperforms everything. Like if we have that fitting SIFT index, if we need to do heavy reads on a table, heavy sum calculations or counting, the SIFT key will make that blazing fast. Now
let's look at the other side.
Now the writing and updating. Now this is the chart now inverted. How long it takes to actually insert 100,000 rows with and without SIFT keys. So now the blue bar is actually without indexes here. It takes about 10 seconds, 11 seconds. The red bar is with 5 SIFT views. So we already take it to 30 seconds, and then with 10, we almost go to 50 seconds. So an increase of almost 40 seconds, or what is it, 400%, by adding 10 SIFT views. So we really should be very careful with adding those kind of read improvements, because we will see the downsides on the writing. And there you really need to decide based on the use case, and then again it depends on your use case, what is happening with the table. If you really have frequent writes to that table and want to increase performance of one read operation, it might not be worth to really go for that super blazing fast SIFT keys, and maybe use a covering index or something to improve it, but not cut so heavily back on the writing operations. Yeah.
And we see that inserts with SIFTs can be pretty slow. But I would argue that these slow inserts are not even the worst problem that can happen when you have multiple SIFTs. Or actually, it can be just a part of a bigger problem. And the bigger problem is the frequency of these dreaded messages. That your session was deadlocked with another user. Or a similar one, there is a log timeout and your session was interrupted. The risk of running into this scary message increases manifold when you have multiple SIFTs, especially in environments with multiple concurrent sessions, with multiple updates, where there are many records inserted, updated in parallel sessions. Why is happening? I said already that SIFT is almost a table, but there are significant differences. Because first of all, the way SQL Server handles logs on the when updating SIFT is much more aggressive. So instead of placing a log row by row when inserting indexes, when updating indexes, you will see granular row logs that can be escalated. Yes, there is a risk. But in case of SIFT, SQL Server will be acquiring range logs, which have, in this case, resulting in much higher risk of conflicting logs from multiple sessions. Add this to the fact that logs will be held longer because of the duration of the updated cell, duration of the insert, it will be much slower, more aggressive locking, and we have a recipe for disaster. Just to give you some context, I have a couple of examples here of these kind of disasters. Case one, a customer running 50 sessions, 50 concurrent sessions, posting around 10,000 transactions a day. These transactions are more or less evenly distributed throughout the day. It's not, of course, completely equal. There are some spikes, like rush hours, quieter hours, but by and large, we can say more or less even. And there are, let's say, 10 to 20 deadlocks per day happening sometimes. And there is another case, 190 sessions running concurrently. And what's making it worse, these transactions are not posted like equally throughout the day. The total number of transactions is around 16,000, which is not hugely different from the first case. like same order of magnitude. But what's worse in this case is that these transactions can be posted in short spikes. Like during the day, it's completely quiet, nothing is posted, and then literally thousands of transactions posted within minutes. And in this case of highly concurrent environment, you see there can be hundreds of deadlocks. And all of these deadlocks happening on 2 tables, which are touched in every transaction. Every transaction asserts certain rows, some records in these tables. One of these tables has 6 SIFT views, and the other one 5 SIFT views. SIFT views. All of the deadlocks happening on SIFT views on these tables. Deleting these SIFT views resolves the problem. Completely 0 deadlocks after this. I'm not saying that, in this case, I didn't delete all of this to achieve this result. There was still 1 SIFT view left on every table, like the most important, the most crucial for reads. And having even 1 SIFT view instead of 5 and 6 on each table resolved the situation. I don't want to say that 1 SIFT view is a safe haven, like say, define only 1 SIFT view on a table and it's secure. Of course, again, I don't know what time we're repeating this, for how many times we're repeating this. It depends. It depends, of course, on the intensity, on the number of parallel sessions. It depends on the data distribution, how many distinct values in every SIFT you have. We can easily construct a SIFT view that will be deadlocking on every session, every time. But on the other hand, if you have like millions distinct views in a SIFT view, probably it will be safe. But for me, like a rule of thumb, if I need to declare 1, 2 SIFT views on a table, still okay. More than 2, probably we need to stop and think about it. So from this perspective, from locking, SIFT can be a source of lots of problems, many problems.
Okay, again, example time. Now we have GL entry. Again, I believe it's almost the same query, just not a find first, but a calc sums instead of the amount column. And as we can see in the resulting SQL query, now we're not even querying the table anymore. It says something about the table, but then we have a long GUID, and we have a vSIFT key 2. So that's because we're using the SIFT view, the SumIndexFields from the defined key number 2, instead of reading from the actual table. And then we can see in the execution plan, again, there is something about clustered index seek, but we have a view clustered appended. So that's the indicator that we are reading from the SIFT view. But as the name suggests, it's an indexed view. So there is a clustered index on the view, and we are using that one to read. Just so you know what you're looking at if you see those kind of execution plans. And then also if we check the key definition in SQL Server Management Studio for that key 2 on the SIFT view, we can see that the primary key columns for that clustered index are GL account number and posting date, just as defined. So everything's there. We can everything check and look up, and that's how the runtime when you do calc sums, like any query which is fitting for a SIFT index, will automatically redirect and read from that structure from the SQL Server instead of referring to the main table. Now, non-clustered index, Columnstore, non-clustered Columnstore index, NCCI. That's, I think, one of the newer kids in the round. Let's see what that is about. And there's a quote we grabbed from the documentation. So I don't know who wrote it, it's just Microsoft. And Microsoft saying that the non-clustered Columnstore indexes is envisioned to be the successor of the SumIndexField technology, which means more or less we don't need SIFT anymore because we have the NCCIs now. And in this part, we will have a look at if that's true or not.
Yeah, and here probably before starting to talk about the impact of Columnstore indexes, how they can be used, we need to explain probably what it is because it's not so common, not so well known. And in the introduction part, I already said that not every index is made equal. they're designed on different bases, on different data structures and for different workloads. And Columnstore index is exactly that kind of index which is not based on our customary usual tree structure. Actually, a Columnstore index.
I mean, the name suggests, now we were talking all the time about row store indexes, now we're talking about column store indexes, right? So it's fundamentally different.
Fundamentally different, and fundamentally, what is actually fundamentally different? That there is no structure that supports fast seek operations inside this index. And what makes it column store is because every column that is added to this index is stored and accessed by the database engine separately and independently. You can think like I tried to illustrate this with this series of bricks. It's called what column store index is. So when we add a set of columns to the index, every column will be indexed or compressed and stored separately. That's one dimension of this index, column. On the other hand, it has the second dimension, which is row group. Row group is actually the set of values from this specific column added to the index. And each row group contains up to 1 million, or actually it's 2 to the 20th power, I believe. That number is slightly over 1 million values. So whenever we define this column store index, we keep adding values to the table up to 1,048,576. These values added keep adding in the row group. Once we reach this number, row group is completed, sealed, done. It's stored. And the database engine continues with the next row group.
Next brick.
In this case,
the next brick. Like
next brick. The next brick of the index. Exactly. So in this way, we end up with this kind of segment structure. It is each kind of what I'm calling brick here is called officially a segment. A segment of an index of a column store index consists of 2 dimensions: a column and a row group of 1 million rows. Not rows, actually values from this column. What makes it more efficient compared to the classic indexes? It's a high degree of compression. Now we're moving to the next slide of pros and cons of it. The high degree of compression, independently stored values of each column. So whenever we query some values from a table, we always have a limit, the query to a certain number of columns. And every column that is requested by the query will be extracted and read independently, and nothing else will be added. Those columns that are not included in the query will not even be read and touched, because every column is stored separately. Database engine SQL Server employs advanced segment elimination techniques that allow the database engine actually to limit the number of segments which will be read during the query execution. And this also can improve performance by limiting the amount of data that will be read. I already mentioned the high degree of compression in this index, and this also results in, of course, less data stored on the hard drive and fewer input-output operations, fewer disk reads. So that's also...
So if I may recite with my own words, if you imagine you have this column chunked into blocks of 1 million records, first of all, you need to have many records to be able to have multiple chunks, but then SQL Server with magic is able to eliminate some of them. So now with that index in place, SQL Server does not have to read through all 10 million rows, but maybe just 4 or 5, depending on how efficiently it's working.
Not 4 rows, 4 million rows.
Million rows, sorry. 4, 5, 10 million rows. So yeah, so it can eliminate some of those blocks and then read a little bit faster, because it doesn't have to read all of them, all the values from that column.
And why I emphasize this, not 4 rows, but 4 million rows, is because now we're slowly coming to the cons, like downsides of the column store index. It doesn't, already was talking about this, that it doesn't support seek operations inside the index. every time we query something from a Columnstore index, it has to do at least one segment scan, meaning it reads these million values from a segment. The whole segment must be decompressed, and these million records will be analyzed to find the record we are searching for inside this 1 million.
The value. The value we are searching for, values.
So because of this, Columnstore index is not really suitable for small queries that extract specific small subsets of data, pinpointing certain record, certain value, because as a minimum, well, we're talking about large tables here, right? So as a minimum, it will scan at least 1 million values in a column. So as I said, the segment elimination technique can make it much more efficient, like compared to scanning the whole table, of course. But on the other hand, there is a downside. Like probably it's so far it's a bit of a problem on the Business Central side. Columnstore indexes are not ordered. In SQL Server, this problem is fixed in the latest versions in SQL 22 and 24 onwards. Columnstore indexes can be ordered, but so far it's not supported in Business Central, and this means that our data that we store in a Columnstore index is not sorted, and whenever we insert the data, with time, our values, our records in the Columnstore index will be spread throughout all segments. And segment elimination, this magical technique that SQL Server employs, becomes less and less efficient with time. So when we have all the data spread throughout every segment, elimination cannot happen. And actually, query executed against the Columnstore index will have to read the whole table anyway. So maybe there is still some development to do.
There are like two scenarios where the Columnstore indexes really bring a benefit if you have lots and lots of rows, like many million rows, or lots and lots of columns, and you have a few columns index, right? So it doesn't have to read the entire, like if you have a normal select statement and it reads the entire table, or it scans the entire table. In comparison to that, the Columnstore index will just scan that one column instead. So if you have many columns and many rows, then it really comes in handy, or can come, depends, right?
So on the positive side of Columnstore index, its impact on, like again, we're returning to our lovely charts. On its third side, its impact is not as dramatic as when we have row store indexes or let alone SIFTs. Like here, back to our benchmark, we're inserting 100,000 records, and adding 5 or 10 fields to a Columnstore index increases by respectively like 7–8% each time, but there is an overhead, yes, of course, for index maintenance, but it's not as big as in case of row store indexes. And when we can use and when we should not use this index, let me start from the not part, the negative part first, when it's not applicable, not suitable. First of all, if we want to find specific data, pinpoint, like small subset of data of table rows, very likely it will not be used at all, just ignored. It is good for aggregations, for large aggregating query, but again, it's not the kind of aggregation query when we run calc sums, let's say, in a loop, every time extracting small subset, just a few records. It will be just grossly inefficient in this case. A covering index, like have a comment here, the covering index will be much better option in this case. This code snippet that I'm showing here is exactly an example of when a Columnstore index is likely to be very, very inefficient. So I have my table, same table with indexes, my benchmark table, and the list of dimensions. Well, I just loop on list of dimensions and run calc sums in the loop. The table itself has just 1 million rows, and every call of calc sums summarizes around 1% of all the values in this table. So every time calc sum is called in this example, around 1% of all table data is retrieved and summarized. So we see this is timing. How long it takes to calculate this, to run this query first without any indexes at all, and with Columnstore index. You see, it's just marginally better than having no indexes at all.
Here, in case you don't see, these are the other times, and we are in milliseconds, so this is 18 seconds, and here we are at the SIFT key, I believe.
Yeah, see, in this case, when we run multiple queries, every time extracting small piece of data from a table, well, don't even look in this direction. But we can continue building up on this example and continue developing it. So here, I'm running this example on, I think it was on my Docker container with SQL Server Express, which doesn't support parallel plans. Anyway, this was single-threaded execution. Definitely no multi-threaded, no parallel plans. When I run it on a developer edition with max degree of parallelism set to 6, well, it becomes even more interesting because now the execution with Columnstore index is much worse than not having any indexes at all. Actually, again, when we look at the total query cost from the point of view of input, output, and CPU consumption, CPU time, this may be more expensive compared to the Columnstore index, but the execution time from start to end will be slower, is likely to be slower. What happens and why? Just because the query optimizer considers the clustered index scan to be expensive enough to trigger the parallel execution plan, while Columnstore index is a little bit cheaper, it's not so aggressive, not so expensive, and it doesn't exceed the threshold for parallelism. It still runs in a single thread. I can play along a little bit more and set the threshold for parallelism to 1, as low as 1. Sure, not something we want to do in production. And if we're running in SaaS, not something we even can do, right? But just for the sake of a demo, I can do like this. I set a threshold for parallelism to 1, and now the picture changes dramatically, because now my row store index read is much faster. It's much faster than reading the clustered index without non-clustered indexes, and it's even better than having a row store index, which is close to a covering index. Because in this case, it is an illustration of the fact that column store indexes are designed for parallel processing. So in this case, the optimizer decides that, again, now in this situation, the query cost exceeds the threshold for parallelism, and we can run the parallel plan. And when it is processed in parallel threads, it's rather efficient. So we can't use it in production, as I said, not something we can do, drop the threshold for parallelism so low, but we can draw some conclusions from this fact, actually. When column store indexes can be efficient, can be used. First of all, we're talking about large tables, talking about millions of rows, first of all. The query itself must be expensive enough to trigger parallel execution. And the query should return like is expected to return. It's not something run in a loop. We prefer a query that will return multiple values in a single run. Group by, typical group by query. And this is what we see here. This kind of query, we define a query object which run a group by SQL query. It's likely to satisfy these requirements. So as long as we have these requirements like matched, running a large table, expensive query, group by, it runs, retrieves all necessary data in a single column store index scan, it will be really efficient. It will be this efficient, actually. Here we have a row store index, and the column store index is much better, almost like more than 3 times faster. And even close to SIFT, still not reaching the SIFT performance, but on the other hand, if we balance everything, positive effects on the data aggregation and much lower impact on the inserts, probably it looks like a good option.
Okay, the last one, and then we get to some examples. And there's a really short one. It made it into the slide this morning because we realized we missed one. We have now the full text index, which is basically the optimized for text search property. This will also create an index on SQL Server, which is called full text index, and it's there for making natural language search or keyword searches more efficient. And you can do some sort of wildcard filtering for entire words, and it will increase those kind of filtering, wildcard filterings, and it's not so heavy on update operations either. So it's a very good option, but still it has a performance overhead. So you don't want to set that on just every text field you have in your table to make the nice full text search in the list view better, because it does have an overhead. But yeah, that's all we were able to fit into the slides. So let's continue with how to find out whether your query is actually using, like SQL Server is actually using an index you created for your query. So there are different questions you need to ask. First of all, it depends on the data structure you have, whether you have nicely distributed values in the column you're filtering on, or if you have like a Boolean with basically two options and 90% of them are true and just some are false, or the other way around. Whether you have lots and lots of records in your table, or you don't have that much, just a few thousand records maybe. And also the query cost itself. So how's the query constructed? How expensive is it? Does it pay off to have the key lookup essentially? Or is it just too expensive to do the matching between index and table, so it just reads the table instead because it's faster that way? And the idea is, if you want to reproduce and test this in your dev environment, you need to create good demo data. First of all, enough demo data, and then also you want to try to match the data structure as good as possible as it is in production. So if you have dimension values in your table, for example, which are basically distributed equally over all the values, you want to do that. If you're heavy on certain values, you want to simulate that as well. Try to really simulate the real data as good as possible, or even take real data and just multiply it or whatever. Then for date fields, are they random, or is it like a posting date, chronologically increasing over time? You want to really simulate that, right? And then how you can actually check this. So first of all, with the debugger, we now have the option to really look into the SQL statements that were sent against SQL Server, and I think 95% of the time it actually is what happens. So you should be able to use that. So you want to do breakpoint, of course, on the statement you're expecting or you want to look into. You need to step over that statement, and as soon as you step over, you can look at the debugger on the last executed statements. And don't ask me why SQL statement number 9 is the last one. In that case, I think you can configure how many you want, but the last one of the highest number is the latest statement that got executed. So you need to grab that. I just ran that through my formatter, and then you end up with a query like this. And depending on how much values you're filtering on, you get those kind of parameters. So you just need to replace this in SQL Server strings, or just like in AL with single quotes, so you can just insert the values you were actually filtering on, because that's not part of the query you can actually receive. So that way you can connect to your SQL Server in your Docker container or whatever, with SQL Management Studio or Azure Data Studio, whatever you prefer, and you can activate the execution plan. There is a predicted execution plan one and the actual execution plan. And this one you want to activate. And then once you run the query, you see the execution plans like we showed you before. Now, this is one other thing you can use to find missing indexes in the system. SQL Server has statistics and statistics over executed queries, basically. And it can recommend to you if indexes are missing to create them. And that view got exposed to us in the web client, so we can actually have a look at what indexes are missing. Unfortunately, we do not see the impact, because SQL Server also knows the impact of those missing indexes.
Knows, I would be careful about
Predicts.
using the word knows.
Predicts.
Yes, estimates.
It depends. So you can get some hints from that table of what indexes might be worth adding to your tables. So you can have a look at those as well. And then, no, it's too small on that screen. Yeah, that's telemetry. So you can also have a look at your telemetry events you're receiving, whether there are slow-running SQL statements. So maybe from your extensions, you see some queries here, other queries, basically, which are running slow, which means exceeding 750 milliseconds threshold. And then you can look into that. Maybe it's AL code, maybe you're missing set load fields, whatever, but maybe it's also missing index you might want to create to increase that performance. Yep. And then we have some more examples, I believe. Do we have time for examples?
Oh, well, we can show some examples, or we can switch to Q&A. Well, we can show these couple of examples, just which kind of index can be used, what kind of code we run, and what execution plan will be generated, what index will be used. The first one, you see, just a very simple one, the simplest possible probably. We set a filter on a detailed customer ledger entry, 2 filters on the customer and the entry type, and we have a suitable key for it, for index entry type, customer number and entry type. And here, yes, this is what we expect this index to be used, and indeed, yeah, it is used. SQL Server runs an index seek on exactly this index to find the data we need. There is one a little more complicated, more interesting example. So here I select data from GL entry, filtered by GL account number and the posting date. What kind of index would I want to create to facilitate this search? There are 2 actually possible candidates if we look in the base app. Which one of these will be used? One has GL account number and the posting date, and the other one 2 fields in the reverse order, posting date and GL account, and dimension set ID as well, included in this field. In this case, actually, what happens, in fact, on this data? The SQL Server Query Optimizer prefers this, key 10, right? Just because key 2, actually. My bad, sorry. It prefers key 2 simply because it's smaller. And it requires fewer input-output, fewer discrete operations. But, in fact, why I was so drawn, so my attention was on key 10, actually because key 10 could be more efficient for our searches if it had only 2 values, posting date and GL account. Okay? It's because posting date, if we have data posted throughout long period of time, right? And GL accounts, normally, especially if company is not too big, we have not too extensive chart of accounts, maybe a few dozen distinct values. While posting date, distinct values of the posting date grow with time. And if the company has been operating for 10 years, we'll have hundreds of distinct values in this field. And in this case, this field is less selective and preferred to be in the front of the index and will be more efficient. Although, exactly in this case, performance difference can be marginal.
It depends.
It depends.
Right. I think we'll skip that example because we want to get to the general considerations, some things, just to wrap it up slowly. So more is not always better, actually. It's often worse. So you want to create your indexes really and test them to be sure that you really need them, because if you create them just in case, it really can slow the system, probably will. So when planning indexes, we should consider updates as well as reads, because if your table sees, like, if you have some statistics around that will be open on Fridays or just on Mondays or the end of the month, just once or twice, then it might be not as worth it to create an index to speed that up compared to the writing and updating that happens on a daily basis all day long, basically. So we should use query objects when developing, just to be able to get the most out of those indexes, to not create so heavy indexes, to somehow make it a covering index or something, because we can predict the resulting SQL query in a better way. And then some recommendations of what kind of index preferred in various situations. When we are searching specific records, aggregations, of course, table joins might also benefit from indexes, but again, it depends. You need to test this really, and there are some fields which are the fields which are filter on that way should be the beginning of the key. Alex just explained that sometimes the more selective field at the beginning makes more sense than if it's somewhere in the middle. So the order of the keys is also important. You might not want to include fields which have the same value. Like as I said, if you have a Boolean which is like in 5% cases true and otherwise just false, it doesn't really make sense to include that. But same goes for text fields. If they are just all empty and there are a few values in there which are filled, then the index can't really make much out of it. You can try to combine filters for several different queries into one key. That can work, but doesn't always work. You need to test it. And then decide, as I explained, against or for index usage based on whether you're writing more than you're reading or the other way around. And that's it.
And we have a few minutes left. Thank you very much for your attention.
Thank
you. The first T-shirt and the microphone.
Hey, an open question. If you don't work on SQL, like on-premise at all, and you only work on cloud, can you still plan your index when you don't have full access to all the statistics? Long-running queries are not always the ones that show the bad indexing problem.
Yes, well, an open question, as you said, yes. It may become more difficult, but still, there are tools that you can use. There are index suggestions. There is telemetry, lock-in telemetry, deadlock telemetry, long-running queries telemetry. And after all, when in a situation when I need to analyze something, difficulties, even when after I have collected telemetry data, I try to simulate the data. I have like scripts that will generate data similar to what customer is running on. After all, performance problems do not depend on some specific data, right, on a specific customer. Likely it's the patterns in data we are looking for and patterns in data access sessions. I use BCPT to simulate the workload and capture these performance problems. Well, yes, it's more difficult, but we still can do it. There was next question?
I have two questions. First,
one T-shirt.
In first controversial example, you said that when it decreased performance, if we add another field to index, will it work better, so it covered the index, or it still
no.
can't work parallel?
No, it's not decreasing performance, I would say. It increases the total execution time, total runtime from start to end. But SQL Server query optimizer doesn't evaluate queries, doesn't estimate performance plan based on pure execution time, right? It estimates based on the execution cost, which includes total CPU time, input-output cost, and many other factors. And plus here we have that fast 50 option, which takes precedence. So whenever, I think adding, I don't know the exact answer, I didn't test, but I think adding another field would not help, simply because, again, it depends, need to test. But just trying to replay this scenario in my mind, I'm thinking that it won't have that big impact, because here preferred execution plot would be still scan the non-clustered index and read the top 50 rows as fast as possible. And that's the premise of this longer execution time, because we still need to run on the non-clustered index and then do the key lookup. And it cannot be parallelized. That is the issue. The shorter execution time for the clustered index scan is exactly because that execution plan can be parallelized. It contradicts the fast 50 option, cannot satisfy the fast 50 option, but it can run parallel threads. That cannot be done for non-clustered index. I guess, so far I'm guessing, but I think no, it won't help.
But in this case, it will not access primary key at all, primary index. It just go by this covered index.
No, so. It will be index seek and key lookup, yes.
Okay. And second question, this NCCI index, how to specify it in BC? Is it new property or?
Well, it's not so new, but yes, it's table property.
It's a property on the table level where you just define the columns you want to be covered, want to have covered.
Okay, it's something new, or we can already use it?
You can already use it. It's
okay.
No, it's been there for quite some time. Yeah, we'll use it.
Okay, thank you.
Oh, there.
I'm not sure if we need to take the questions to the front because...
Lady first? Sure.
Yeah.
What would be your general recommendation for buffer table that generally has a lot of writes per day, like let's say 1,000 lines, but at the same time, based on specific criteria being updated by users in the Business Central? And being, because it's a buffer, being copied to another table.
But buffer table, you don't mean temporary tables. It's actually stored on SQL Server. The recommendation, I believe the recommendation, because these tables should be, I would say, optimized for faster writes. Right? We don't expect to read or aggregate any data from this table. So I mean,
the users will be reading the data and updating certain things. So they will be so they will be read by the users, the end users.
Okay.
Sorry,
I'm going to say. Sorry for what I'm going to say, but I want to say it depends again. What do they want? Depends probably what users want to read. If it's a buffer table, like many records inserted in this during the day and maybe in heavy write load, I would try to minimize the indexes at all, and then I would look what kind of read operations, what users look for in this table. Is it some kind of specific rows they want to update? I believe you mean they want to update something manually, right?
Yeah.
Well, then it can be optimized, depends on how they search again. Filters, we don't want to add index or to facilitate all kinds of filters, right, on every table because it will slow down all our updates. But maybe some most important, they don't want to access records inserted months ago, right? Probably index on the date, first of all. Look for to be able to filter by the date. But try to minimize the overall number of indexes here.
Okay. One last T-shirt. Maybe there. Yeah.
Someone in the back?
Index performance is a lot of dependent on fragmentation of index. And is there any future plans of Microsoft of letting us know more insights about fragmentation and the possibilities to actually do some maintenance on it?
I think I know the answer to that one. No. And the longer answer is Microsoft's taking care of the platform, and we should not worry about the underlying structure too much. They have routines and everything that figure out when a rebuild is necessary or a maintenance job, and they will execute that on as it's needed. So the plan is not there to dedicate this to us in any way.
Too bad.
Sorry.
We're out of T-shirts, but okay, so yeah, we're done.
Thank you very much.